Okay, so let's get started. A little bit of robotics gossip for a moment. Boston Dynamics produced Big Dog and Alpha, the new biped robot. Google acquired Boston Dynamics last year, and as of a couple days ago, they've sold them off. You're all becoming robotics experts now. Anybody want to take a guess why Google has lost a little bit of taste for robotics?
Make a product that they can sell to people.
Not yet, right? Alpha is going to be a little bit more than Lego Mindstorms, right? So perhaps Big Dog and Atlas will be useful someday, but not quite yet. Anyways, you can go and see what the pundits have to say about it. Just thought that might be interesting to some of you. Okay, so back to evolutionary robotics. We're working our way through this theme of challenges, open problems in the field. Again, one of the reasons why Google might have sold off Boston Dynamics. There's a lot of open questions out there about how to try and scale up, in our case, an evolutionary approach to robotics to very complex and adaptive machines that can get along well with us here in the real world. We spent a bit of time a few weeks ago talking about genotype to phenotype mappings. Can we set up our evolutionary simulation in a way that we have an evolvable system, which means if we keep running our evolutionary algorithm for a month, it will continue to produce better and better robots? Still an open problem. We're now talking about the reality gap problem. We evolve robots in simulation. We transfer one of our evolved solutions from simulation to reality, and as you all know by now, that usually doesn't work. We talked last time in lecture 16 about the radical envelope of noise hypothesis. One of the reasons why the reality gap exists is not just because the simulator is not a perfect reflection of reality, but because evolution is an exploiter, right? Evolution will find a way to exploit inaccuracies or simplifications or approximations in the simulation, and obviously those exploitations are not going to work when we transfer to reality. So one of the early ideas in the field was let's add a little bit of noise to the various physical phenomenon in the simulator, and let's specifically put noise on those parts of the simulator that we know the simulator is not going to do very well. Okay, what's the problem with the radical envelope of noise hypothesis? We're going to obviously talk about three more recent approaches, so this wasn't the best solution. Why isn't noisifying the simulator enough to ensure that we can transfer things from simulation to reality? There are other sources of error, such as? Absolutely, right? So we might have an idea about some aspects of the simulation that should be made noisy, but there may be other aspects that we're missing that we didn't noisify.
By taking the most minimal approach, we're designing a robot for a situation that's almost too much in the opposite direction.
Right.
Too unlike real life.
Exactly, right? So we're gonna start to deal this week or next week with issues of scalability, right? So in the radical envelope of noise hypothesis, this was back to the 90s. They were working with the little wheeled Kepler robot, which is all well and good, but what happens if we want to create a simulation of Atlas, right? A biped robot with hundreds of motors and thousands of sensors that gets around in a very complex environment. We'd have to make a very complex simulation that would have lots of physical phenomenon that we would have to try and noisify, which is going to really slow things down. Okay, so a good first start. We're going to tackle some more recent approaches in a moment. But before we do, we're going to talk about the assignments and the final project. So has everyone completed the 10th and final assignment? Okay, so your Python code is talking to your C code and vice versa. So you're now able to evolve a robot who's managed to evolve a robot at least 5 units away from the origin. 6 units, 7 units. 8, 9, 10. Who's been able to get beyond 10 without their robot cheating by exploding or doing something that you didn't expect? So far, so good. All right, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. What did you guys get to?
32.
32, pretty good.
Somewhere like 51, 52.
Okay, 50, 45.
34.
Okay, did you guys make changes to the simulation beyond the specifications in assignment 10? Okay, so
Wait, how many generations?
how many generations? Oh yeah, one yes, that's fine.
I was like 230,000 generations.
230,000 generations. Okay, that's good. We have a pretty evolvable system there. That sounds good.
Mine's up to 600.
After about 600 generations.
I got 600,000.
600,000 generations. Okay, excellent, excellent. All right, you're doing your part for fighting climate change, right? So, or helping climate change, right? Okay. So now things get fun because now you've completed all 10 assignments, and all of you should now have a functioning evolutionary robotics simulation that you can run on your laptop. And the question now becomes, how do you want to expand your system to tackle a question we've mentioned in class or some other challenge that exists out there? So we got 6 weeks left in the semester, and that's what you're going to be doing over the next 6 weeks. That is all described in a document, so if you click on this link here in the schedule or in Blackboard, you'll also find a pointer to all of the information about the final project. And I want to spend just a few minutes now going through the basics of what you can expect, but again, all the details are here. So please, either tonight or sometime this week, find some time to go through and read this document carefully. Okay, so the final project is worth 30% of your final grade, and there are basically 3 things that you're going to be doing over the next 6 weeks. You're going to continue submitting material on Reddit every Monday night, but now instead of assignments, you're going to be submitting weekly reports, and each one of those reports is showing us that you're making progress on your final project. We'll talk about what those reports look like in a moment. Again, there's no exam in this class. During the exam period, everyone is going to be presenting their project orally. We have 42 students, and we have, what do we have? We have 2 hours and 45 minutes, so it works out to about 3.5 minutes each. So these are going to be very, very brief oral presentations. We'll talk about them later. You'll also be submitting at 11:59 the night before the exam period a written report which will summarize your final project. And again, we'll talk about that later. Basically, what you're going to be doing now is creating an assignment 11. So you're going to be creating an assignment that you are going to implement, but you are also going to write wiki instructions like you followed for the 10 assignments. And one of the things that we're going to be looking at in your final project is this something that a student next year could implement, assuming that they've completed assignment 10? So there are sort of 2 things we're looking for in your final project: that you implement or you expand assignment 10 in an interesting manner, you add some additional functionality, and you explain it well to a hypothetical student in next year's class. Right? That's the basic idea. Okay, so obviously that's exactly what the students did last year, so you've probably all noticed this by now. On assignment 10, you can now see that there are next steps, and they branch out in all sorts of different directions. Some of you may or may not have already seen the course tree. This is a visualization of all the material that's available on the subreddit here. So all of you started on day 1 of the class here. You completed the 10 assignments out here. Here's assignment 10. And then assuming that you have assignment 10, here are all the assignment 11s that students made last year, right? And we'll now obviously be growing this list. Okay. So the first of the 6 weekly reports is choosing your project. And again, this is something you're going to be submitting on Reddit next Monday. And basically what I want you to do is have a look through all of the projects from last year. I listed some additional ones here to give you a feel for the kinds of things that we're looking for. So, for example, I think there's a running example in this document about evolving the robot to jump. So that's probably something that is not going to take you 6 weeks. Assuming what you have now, imagine you needed to alter your assignment 10, so instead of evolving for a robot that locomotes into the screen as far as possible, You select for a robot that jumps as high as possible. What do you need to change in the simulation for that?
Just change the fitness to Y.
Okay, so now you maximize Y. What might you get? Are you going to get jumping?
You get like
You'd probably get standing, right? So remember that it's integrating whatever the coordinate is over time, right? So it's not as trivial as that. What else do we need to change about the fitness function to get jumping?
You'd need to check the highest point at any time over the simulation, not just the final endpoint.
Exactly, right? So now we get into fitness function engineering. You probably want to select what was the maximum value of the Y coordinate over the 1,000 time steps that you evaluate the robot. So it can stay low for however long it wants, as long as at some point it maximizes the Y coordinate, right? So evolving a robot for jumping is probably not a good choice for your final project. It's too simple, right? A couple lines of code, couple hours of simulation, and you're done. Okay. So what I want you to look for is sort of the amount of functionality that we're looking for in these projects. So it's just one example. You might want to take your legged robot and turn it into a wegged robot. So a wegged robot is a robot that has legs that are appendages that are both legs and wheels. So again, you'd have to now make some change to not the fitness function, but the body of the robot. So for some of you in your final project, you're going to be having to change the body of the robot. You're going to be having to change your Python code because you're going to be changing the brain of the robot. Some of you are going to have to change body and brain. Okay, what might be the advantage of a wegged robot over a wheeled robot or a legged robot?
You can go faster over smooth terrain than a legged robot, but it can still go over rough terrain like a legged robot.
Exactly, right? So you could change your legged robot into a wegged robot and then change the ground topology in the physics engines to demonstrate the advantage of a wegged robot. Maybe you take each controller for your wegged robot and evaluate it twice, once on flat ground and once on rough terrain, and see that it uses wheels on flat and legs on rough, right? That would be a good example of a final project. We haven't got, there's a bunch of topics obviously that we haven't got to in the class yet. You can look ahead. We're going to spend some time talking about collective intelligence or robot swarms. You might want to try and create not just one robot, but multiple robots and evolve the robots to do something that would be beyond the ability of any one robot. Yes?
Would developing a more efficient evolutionary algorithm, maybe using neat, and then just applying it to the walker?
That would also be perfectly fine. So if you're more interested in the evolutionary side of things that we've been talking about so far, you can swap out the very weak evolutionary algorithm that we have at the moment, evolutionary algorithm, because there's just one, there isn't a population, and replace it with something more powerful like neat or hyperneat. If you want to do that, that's fine. There are existing software libraries already out there for neat and hyperneat. Again, it wouldn't be sufficient to just use something that's already off the shelf. If you want to try and implement neat or hyperneat on your own, that would be great. And again, you would want to demonstrate why you would want to do so by demonstrating that neat or hyperneat would do a better job of evolving your quadruped than the hill climber does. Okay. So again, collective intelligence. If you go back and look at the ragdoll demo, you can actually see how they set it up so that it was easy to create not just one ragdoll, but multiple ragdolls. You might adapt some of that code so that you can create multiple robots, and again, have them to do something that's beyond the ability of any one robot. You might leave the body plan of your robot the same, but change the environment and change the fitness function. So this was a admittedly aborted attempt to evolve stair climbing. You can try that one out. More difficult than you think. So watch this video and you might be able to get a feel for that. A lot of students have done that one. That one's pretty challenging. Let's see, what else? You might want to add a gripper to the quadruped, so combining locomotion and object manipulation. That might be another thing to try. What would be a fitness function that selects for good locomotion and object manipulation? Let's see. This is one I always add to the list, hoping someone will take. No one's taken me up on this offer yet. Hans Moravec was a very famous roboticist at MIT back in the 1980s. He proposed the Bushbot, or a fractal robot. This is a drawing of what a fractal robot may look like. Every arm has 3 arms attached to it, all the way down. You can imagine that there are things that a fractal robot that could do that would be very difficult for things that have this kind of body plan. Fractal robot might be able to manipulate many, many more objects. Again, this was my attempt to sort of sketch out in simulation some beginnings of a fractal robot. Would obviously require some significant changes to how you simulate the body. Let's see. Turn the quadruped into a wheeled robot and evolve it to chase a moving object. Again, when we get to collective intelligence, we're going to look at predator and prey robots. One robot that tries to run towards another object, another robot, and that robot has a different fitness function, which is run away from the robot that's chasing him. Okay. Evolve a robot to brachiate. So we're having technical difficulties, so I'm not going to be able to show you that one. Brachiation is the ability to swing from tree limb to tree limb. I showed you that video, I think, at the beginning of the course. Another thing you might want to tackle. Bipedalism. Remember our discussion about legged locomotion. Bipedalism is not trivial, but it is possible. If you want to try and tackle some form of passive dynamic walking, that's possible as well. I would suggest you try not to combine these two and do bipedal passive dynamic walking. Perhaps stick with the quadruped. Your quadruped at the moment is incapable of passive dynamic walking. What is the minimal amount of change you would need to make to assignment 10 to evolve passive dynamic walking, or at least hybrid dynamic walking? Could be an interesting one to try. And again, a list of all the project ideas from last year's students. Okay, so you can have a look through these and to get an idea for what's possible. Okay, so once you have an idea for what you want to do, by next Monday night, you're going to be creating a submission again in the subreddit. Once you have, you're going to go back to Blackboard and embed the URL that points to that Reddit submission. But now, instead of a submission, you're going to be submitting a project to the subreddit. So you need to make sure that when you create a submission in the subreddit, you add this prefix instead of the submission prefix. That's actually read by the bots that we use to maintain the subreddit. So that's a specific kind of submission. When you create a project submission, you will get a response from a bot that will create a wiki page that mirrors your submission, right? So in all the 10 assignments, you've gone to the Reddit post for assignment I, and behind that is a wiki page I that corresponds to that Reddit page. So every Reddit page that's a submission also has a wiki page created for it. So what you're going to be doing is creating a project stub by submitting a project to Reddit. When you do, the bot is going to create an empty wiki page for you, and that empty wiki page will look like this. There will be a stub for prerequisites and a stub for next steps. First thing I want you to do is go into the wiki page, change the stub for the prerequisites, so that it points back to assignment 10. That will, in essence, connect your assignment 11 to assignment 10. So far, so good? Okay. The rest of the wiki template looks like this. So there's the title. all you really need to do for next Monday is write a couple sentences to summarize what you plan to do in the final project, right? So evolve a jumping robot. The goal of this project is to build a robot frog simulated in a physics engine and evolve a controller to enable it to maximize its locomotion through hopping or jumping. So this is actually combining locomotion and jumping, right? We don't need a lot of detail here, but just enough to sort of see what the basic idea is. You'll notice then that there's an empty stub for project details. Over the following 5 weeks, you're going to be filling in just that project details part of the wiki with a whole bunch. Here's the project description for one class, for one project. Actually, let me pick a better one here. This should be in project details. Anyways, you get the idea. You're going to be filling in an indented, bulleted list with all the instructions about how to implement your assignment 11. Okay, again, this is all described in the document. So far, so good? Okay. Okay, so what we want to see by Monday night is that you've created a project in the subreddit. The bot will create an empty wiki page for you, and we can see that there's a couple sentences describing what you have in mind. Okay. The following week, you're going to be going in and editing your wiki page and breaking it into a set of bullets, and each one of those top-level bullets describes the milestones. So the key to success for the final project in this class is pick something that is maybe a little bit ambitious, but at least you have in mind very clear steps in how to get there, right? So for example, if your final project is to create wegged robots, what is the first step that's going to take the quadruped and start to turn it into a wegged robot, right? First step could be turn the robot into a wegged robot. Step 2, evolve it to do something, to evolve over flat ground and rugged terrain. That's not a good first step because that step is too high, right? We want to create a large number of very small steps. The first milestone might be to create a cylinder, and it's a cylinder that just sits next to the front left foot. It's not even attached, it's just an additional object, right? Remember in assignment 5, you were just creating one object at a time. Assignment 6, you created one joint at a time. Assignment 7, you motorized one joint at a time. Very, very small steps. So take your quadruped. Step 1, put a cylinder, a short cylinder right next to the left front foot. Maybe step 2, add 3 more cylinders that sit next to the other 3 feet. Step 3, attach each of these cylinders to the foot with a rotational joint, and so on and so forth, right? Lots and lots of small steps that will gradually change your legged robot into a wegged robot. That's something that we're really looking for when we assess the final project, that you have an end goal in mind, and even if by the exam period you don't manage to get through all the steps and get to the final idea you had, but maybe you sketched out 17 milestones and you got through the first 11, that's fine, right? That's much better than saying, here's our final goal. I had 2 big steps and I didn't manage to implement either of them. Okay? So think very, very carefully about what you want to do. More importantly, think about how to break it into lots of very small steps. Okay. So in weekly report 2, you're just going into the wiki and actually writing out as many of those steps as possible and breaking them into as small pieces as possible. By the end of the 3rd week, you should implement the first of your milestones and submit, like usual, a screenshot demonstrating that you've implemented that milestone. At the end of the 4th week, we want to see that you've gone back into the wiki and described that milestone in enough detail that a hypothetical student next year could do it. And then week 5 and week 6 are the same thing. Give us proof that you've implemented milestone 2 correctly, and then give us proof that you understand it enough that you could describe it to a student next year. Now, as I mentioned, some of these milestones may be very small, So if your first milestone is place a cylinder next to the left front foot, that's probably not going to take you 2 weeks to implement and describe the instructions for it, right? So maybe you organize things hierarchically. So maybe milestone 1 is add wheels to your robot, and milestone 1 is then broken into milestone 1.1, which is put a cylinder next to the left front foot, 1.2, 1.3, 1.4, and so on. Right? It's up to you to decide the amount of functionality in milestone 1, but it should be sufficient that it takes you about 2 weeks to implement it and write up clear instructions describing to another student how to implement it. So far, so good? Okay. Okay, I think you can read about the oral presentation and written report. We'll talk about that when we get a little bit closer. What I want to do when you submit your weekly report, the first one, your project idea. Again, you can pick something from this list, pick something that a student has done last year, but of course we would love you to come up with something new that is on neither list. And go ahead and come up with an idea. If it's something that's a little bit too ambitious, we'll let you know in the comments back to you, and that's fine. As long as you have something new that's in mind, I'll give you a little bit of feedback about how to maybe scale that back if I think it's not something that's doable in 6 weeks. Okay. Sorry, one other thing about assignment 10 and 11 I wanted to mention is you now have a fully functioning evolutionary robotics simulation, but it is screamingly inefficient, right? It's popping up a visualization of every robot, takes a while to evolve it. If you go and have a look at the course tree, you'll notice that some of the later projects that are listed down here are projects from last year. Let's see if I can do this by eye. You'll notice that there are projects 17 and 18 here. These are additional assignments that students have written in years past to help you make your assignment 10 a little bit more efficient. As the name implies here in project 17, there's an additional code you can turn on that will make your simulation blind, so it doesn't open up this visualization window every time. So it will simulate the robot, but it will not draw the robot. That will obviously speed up your simulation greatly. You need to implement this in a modular fashion so you can turn back on drawing at the end to actually see what you managed to evolve. You can also, in a relatively trivial way, parallelize your code. Most of you probably have multi-core laptop machines by now. If you do have a multi-core machine, it's pretty trivial to parallelize things. So now your Python code, instead of initiating one instance of your simulation, it can start up 3 or 8 in parallel. You're also going to then have to make changes to your hill climber, right? Your hill climber at the moment has 1 parent and 1 child. You can make some changes to your Python code. So now you have a parallel hill climber, for example. So you have 8 parents, and each parent produces 1 child. You can simulate all 8 child simulations in parallel. Again, assuming you have a sufficiently high-powered machine. Go and have a look at 17 and 18. They'll help you make things more efficient. They're optional. You don't have to. It's up to you. Okay, I think that is all I have to say on assignment 10 and final project. Any questions about that? No? Okay, so let's jump back to lecture now and crossing the reality gap. We talked about the noise hypothesis as an attempt to deal with the reality gap back in the 90s. Today we're going to talk about the GOLEM project. Who or what was the GOLEM? This is from Hebrew mythology, this clay figure that came to life if you did certain things. So the GOLEM project is going to be about robots that are brought to life in the sense of bringing them from simulation to reality. Okay, so lecture 17, the GOLEM project. The original inspiration for the GOLEM project came from this long-term goal in AI and robotics, which is self-replicating machines. Here's an example of self-replicating machines. This is a cartoon from a NASA report back in the 1980s. So this is a very old idea. If we want to use robots to explore or colonize the solar system, it doesn't make sense to build one robot or a couple robots and send them a very long distance. Better to send a machine that when it gets there can forage for the raw materials it needs to make a copy of itself. This idea actually dates back to the 1940s and was originally articulated by von Neumann. You all know about von Neumann architecture, which is the underlying architecture in your laptops and phones. Von Neumann machines were these ideas of self-replicating machines that, again, were sufficiently complex that, given the raw materials, they could make a copy of them themselves. Okay, it's an idea that still hasn't really been implemented in reality, but at least the GOLEM project was a demonstration of a first step in this direction. So the reading for today is the Nature paper actually about this project. It got a lot of media attention, as you can imagine, back in 2000 when it was published and made it onto the front page of the New York Times. The media liked this because they could digest this idea down into machines making machines. The machines in this case were the robot that was being manufactured, and it was being manufactured by a brand new kind of machine called a 3D printer. So this was the beginning of the 3D printer revolution, which demonstrated that you could actually use a 3D printer to make other machines. Now this is not really self-replicating machines because once you build the robot, it can't build a copy of itself, but at least it's a first step in this direction towards machines making machines. Okay, so that's what we're going to be talking about today. This is an evolutionary robotics project. There are three main steps to the GOLEM project. The first one, which we're very familiar with by now, evolve robots to locomote in simulation. Once you've evolved a robot to do so, and we're going to evolve both the body and brain, manufacture a physical version of this robot using a 3D printer. These days, there still is a required third step, which is we cannot yet print all of the basic parts that make up a robot together using one 3D printer. So it is still not a completely automated process. The human still has to come in and snap in this case, motors and electronics for the robot. Okay, so let's start with the more familiar side of things, which is evolving the body and brain of robots. Here's the way in which the researchers encoded the genotype. So the genotype was actually a long string, defined here as robot. That string was made up of 4 substrings that had arbitrary length. The first string dictated the vertices that make up the robot. The next list defines the bars that connect the vertices of the robot together. The third list defines neurons, and the last list here defines actuators. And an actuator is created on the robot when a neuron, which is part of the neural network, connects by a synapse from a neuron to a bar making up the robot's body. Okay. So let's unpack this a little bit more. The list of vertices is a list of triplets, where each triplet defines the x, y, and z coordinate of a vertex. So evolution could evolve robots that have more or less vertices, and mutations can also alter the positions of those vertices. The next list is a list composed of 4 tuples, where the first 2 numbers indicate the indices of the 2 vertices that are connected together. The third number dictates the relaxed length and stiffness of the bar. Where have we heard these terms before? What does the relaxed length and stiffness of the bar tell you about the bar? It's not just a bar. Do you remember our discussion about stiffness and damping?
It's
It's a spring, right? Exactly. So it's not mentioned here explicitly, but the bar is actually broken into two, and there is a spring sitting in the middle of each bar, and that spring has a relaxed length. So there's a particular length that spring likes to be, and it may be a spring with more or less stiffness.
This is a bit of a throwback, but
That's
was
right.
was this a precursor to the sort of, the amorphous robots that you showed us at the beginning of the semester?
The amorphous, oh yes, right, the tensegrity robots. I think the first video I showed you in the course, right? So the tensegrity robots, which are now being built at NASA Ames as a prototype for the next generation robot probes, yes, they're a descendant of this project. Okay, that's where this came from. Okay, so each of these bars connects these vertices together, and there's a spring in the middle, which may be more or less stiff. We have a list of neurons, and so the next list is made up of a list of sublists. We have a neuron, and we have a threshold, and then we have another set of numbers, which are the synapse coefficients that connect to all the other neurons. So there are a number of constraints here. So if we have, for example, in our neuron list 3 sublists, that means that, or let's follow this cartoon here. Let's imagine that our list of neurons has 5 sublists in it. Each one of those sublists tells us about each of these 5 neurons. It's assumed that each neuron is always attached to all the other neurons and itself with synapses. What does the neuron threshold mean? Threshold of what?
Perhaps a threshold of value to actually affect another neuron.
That's
That
it, exactly.
way,
So
that way you won't have everything firing off everything else all the time.
that's exactly it, right? So remember our discussion about neural networks? Each neuron sums all of the incoming values, and then that raw sum is passed through an activation function. There are different kinds of activation functions that we can use. In this experiment, they used just a threshold. Above that threshold, the neuron sends a value out to all of its neighbors. If the raw incoming sum to a neuron is below the threshold, it outputs a value of 0. That's it. Okay. Synapse coefficients, what does that mean? The synaptic weights, right? So what is the strength of connection to all the other neighboring neurons? So the first 2 lists define the robot's body. The third list defines the structure of the robot's brain. The fourth list connects the robot's brain to the body. So again, in the actuator list here, we have an arbitrary number of triplets. Each triplet connects a neuron to a given bar, and it defines the bar range. So in this case now, we're not going to be using rotational joints. We're now going to be using linear joints or linear actuators. So in the cartoon example over here, when this neuron sends a signal, a positive value to this bar, the spring pushes outward and expands the length of the bar. When this neuron outputs a negative value, that applies some force to compress the spring and reduce the length of the bar. So an oscillating neuron will cause the bar to extend and contract, extend and contract. You can create linear actuators in the bullet simulator as well. Again, something else you might consider adding to your robot in the final project. Okay, so that's the genotype, and that's the phenotype that it produces. Evolution can add, delete, or modify vertices, bars, neurons, and actuators. Is this a direct, indirect, or developmental genotype to phenotype mapping? And how do you know? Let's talk about developmental mapping for the moment. Right? A developmental mapping is something that grows a robot over time. So over the lifetime of the robot, the body is growing. Do we have that here? No. So it's definitely not a developmental mapping. Is it a direct or an indirect mapping? And again, how do we know?
It's direct,
How so?
because each of the different numbers corresponds to exactly one feature of the robot.
Exactly. So this is a direct mapping because any one number in any one of these sublists corresponds to just one trait or one piece of the robot's body or brain, right? So it's a direct mapping, but it is not a fixed length mapping, right? We can make robots that are more or less complex by adding or removing material from the genotype. Okay. So let's talk about evolution for a moment here. They started with a population of 200 null genotypes. So they had a null list. So not surprisingly, that produces a null phenotype. The fitness is displacement of the center of mass, so not that different from what you have in assignment 10. The evaluation period they defined in the paper as a fixed number of cycles of its neural control. I put question mark there. What does that tell you about, there's a missing detail about the body and brain of the robot that I haven't mentioned yet. What is it? If one or more of the neurons are cycling over time, what does that tell you that's in there somewhere?
It's going sinusoidal, so we know that there's a
G, right? There's a central pattern generator in there somewhere. So one or more of these neurons is always outputting a sinusoidal pattern, and you'll see that when I show you some of the videos of these evolved robots. You'll see that showing up. Okay, so there's a hint there that there's a CPG in there somewhere. So whatever the CPG is, they allow it to oscillate 12 times, however many time steps that was in their simulator, and then that's it. Okay, so we take our 200 null genotypes, they produce 200 null phenotypes. What's the fitness of all those null phenotypes? 0, right? Okay, take those 200, mutate them, produce some new versions, and now you might have a non-null genotype that turns into a non-null phenotype. One or more of those may manage to move a little bit away from the origin. Okay. Here's a list of all the different mutations that they allowed to be applied to the genotype. So somewhat different from your mutations, which just changed synaptic weight. They had a list of 10 different mutations that were possible. Each of these 10 different mutations had a different probability. So when a genotype was selected and a copy was made and mutations were introduced, they would be introduced with this kind of probability. So a mutation could change the length of one bar making up the robot. It could change the weight of a synapse. It could add or remove a dangling bar to the body. It could add or remove an unconnected neuron to the growing neural network. It could split a vertex into two and add a small, it could take a vertex, split that vertex in two, and add a small bar that connects those two vertices together. Number 8, it could split a bar into two. So you could have a bar, splits into two, add a vertex at the midpoint there. So now we've got an additional vertex and an additional bar. Attach or detach a neuron to a bar. So attach a neuron to a bar, motorizes that bar. So it's now going to oscillate depending on what the neural network is doing, or detach the neuron from the bar, and that actuated bar becomes a passive bar. So we kind of have a combination here of ragdoll and actuated joints, right? Evolution can actuate more or less of the body over evolutionary time. Okay, and they made sure that at least one of these mutations, if not more, was added to each new genome. Okay, so here's a cartoon of a null phenotype, which is nothing. And then each of these arrows indicates that one or more of the mutations from this list was added to this phenotype to turn it into this phenotype. Another one or more mutation was added to this phenotype to turn it into this phenotype, and so on. So just sort of showing you over evolutionary time how null phenotypes can evolve into non-null phenotypes. So just to build up your intuition about how this all works, I want you to turn to your neighbor, and I'll give you a couple minutes to try and label these arrows with the numbers 1 through 10, which are the mutations that actually turn this phenotype into this one. Remember, at each step there may be one or more mutations that does the trick. Make sense? Okay, go for it. We'll see what you came up with.
So that's like a
All right, let's see if we can figure this out. What mutation turned the null phenotype into this phenotype? Change the length of a bar. So no bar yet.
Not null to 1. 1
Okay.
to 2 is 1, but null to 1 is 3.
Add a dangling bar.
Yeah.
That's right. So mutation type number 3.
Then 1.
Then 1. Then
1 and 5.
1, change the length of the bar again, and 5, add an unconnected neuron. Yep, that makes sense. So 1 and 5 got you from here to here. What gets you from here to here? 1 again, so the bar has grown again through mutation, and
Well, 5 again, because we're at, well, yeah, 5 and 3.
so it's a little unclear from this list. So again, number 5, add an unconnected vertex. What's not mentioned here is whenever you add a new vertex, all the existing vertices, add a new neuron, all of the existing neurons send out a new synapse to attach to the new neuron. So you need to go back to the neuron list and add in an additional synaptic wave. Yes?
I actually had a question about that. So when we first add a neuron, why isn't there another little line that's showing it connect to itself? And then the second one, why aren't there? Is it just to save space?
I think they neglected to put it in or save space, so just mentally add that. Okay, what about this step to this step? We've got 1 bar here, and then the next step we have 1, 2, 3 bars. Let's focus on the body first, forget about the brain for a moment. 8? Right, so split the bar into 2 and add a vertex. That's possible. I think what actually happened is step number 7 here. So they take this vertex here, split it into 2 vertices here, and add an additional bar here. Hard to say. Could be 7 or 8. What happened, what mutation altered the brain here? Number 2, change of synaptic weight, exactly. Right? So 2 and 7 or 2 and 8. Number 9, attach a neuron. They pick this neuron and attach it to a bar. They attach it to this bar. What happened to this bar? They changed it into these 2 bars. This is definitely number 8, right? Take a bar, split it into 2, and add a vertex at the midpoint. Make sense? Okay, so a good way to build up an intuition for a genotype to phenotype mapping is to play this kind of game, right? Take a very simple phenotype or no phenotype at all and mentally add some mutations and figure out how the phenotype changes over time. Okay, so you can see that this particular genotype to phenotype mapping is biasing evolutionary search to particular kinds of phenotypes. We don't have bipeds and quadrupeds now. We have these tetrahedral meshes, right? Which NASA is now turning into these tensegrity robots. Another interesting observation about genotype to phenotype mappings, whenever you pick one, you're changing the kinds of phenotypes that evolution is going to explore. If you were to come up, there's probably a genotype here that creates a phenotype made up of thousands or millions of bars that actually is a quadruped or a biped. It's probably going to be pretty difficult for evolution to actually find that in the space of all possible robots, but it's there. Okay. All right, so we just did this. Okay, so let's actually see some of the things that they evolved. Here are some samples from one run. They've done part of the evolutionary run, and then they took a cut through one generation. So these are all the individuals that exist in the population at that generation in this one run. And you start to get a feel for the kinds of body plans that are possible. Here are some samples now that are not a cut from one generation, but it's the best robot at generation 4, generation 13, 26, 27, 36, all the way up to the best robot at generation number 198. You can see that the best robot in the population was always similar, but there was definitely evolutionary change happening and evolutionary improvement. Right? The robot's body was changing over evolutionary time, presumably so also was its neural controller. These are some interesting plots from the paper. Again, something you might want to use in your final project to illustrate evolutionary change. So these are phylogenetic trees. If you've ever taken a biology class, you've probably seen these before. In a phylogenetic tree here, each node corresponds to one individual in the population, and each edge connects a parent to a child. We now have evolutionary time proceeding from the top of an image down towards the bottom. The horizontal axis shows ancestral proximity. So what that means is that two individuals that are close to one another horizontally share a relatively recent common ancestor. Two individuals that are separated by quite a bit horizontally, you have to go a long way back until you find a common ancestor for them. Okay. If you visualize evolutionary change in this way, it's relatively easy to see evolutionary dynamics going on in the population. So if we look at panel A here, we can see divergence. So if you look carefully towards the top, there was one individual here that produced lots of different offspring over evolutionary time. There was another individual way back in the very first generation that also produced a lot of individuals. Two of its children produced a whole bunch of other children and so on. So at the end of this evolutionary run, you had robots that were all different from one another. Some of these robots were different and had a relatively recent common ancestor. Some of the individuals in the population, they have no common ancestor. You go all the way back to generation 0, and this individual evolved from one null phenotype in the initial population, and another individual evolved from a different null phenotype in the initial population. Okay, you go back to the beginning of simulation, run it again. with no change except different mutations being applied, you can get incredibly different evolutionary dynamics, which is one of the cool things about evolutionary algorithms. In this case, we got convergence. So at the end of the population, there were a whole bunch of robots that were very similar to one another, and they all shared a relatively recent common ancestor, very different from this run. Go back and do it all again, and in this third evolutionary run, you got the emergence of species. So there were 1, 2, 3 groups of robots in the final population that were all quite similar to one another, but quite different, large differences between the 3 groups. In this fourth run here, a beautiful example of extinction. So here's the dinosaurs up here. So they were during these generations, they were dominated by variations on this common ancestor. However, there was 1 mammal hiding in the population there, or maybe 3. I guess we got 3 lines here. So 3 individuals that had high enough fitness that they stuck around for a while. They had no common ancestor with the dinosaurs, but they managed to survive for long enough. Then these 3 individuals started to produce some children that had higher fitness than these ones over here, and eventually evolved to the point where they drove the dinosaurs to extinction. And at the end, again, you had just 1 species, which is very different from the individuals that were dominating the population early on. So again, as you're implementing your final project and you're doing a lot of evolutionary simulations, you might think about trying to create these kind of visualizations to see at a glance what's going on in your evolving populations. Okay, let's actually have a look at some of the evolved creatures. There's lots of videos to show you, so hopefully these will work in situ. We're in luck today. Here's a snake. Here's one of its descendants. How did this species evolve to locomote? You could think of this as peristalsis, right? We spent a lot of time talking about how evolution exploits the physics of either its simulated environment or real environment. What kind of exploitation is going on here? What aspect, what physical phenomena did evolution exploit to make this happen?
Friction.
Friction, right? So if you're not a legged robot, you're lying flat on the ground, the biggest challenge for you is going to be friction, right? So how do you minimize friction? You push against the ground, try and minimize it so that it's asymmetric. There's less friction in one direction than the other, and you'll move in one direction, right? Pretty much all of the GOLEM robots have this idea in common, but they all manage to minimize and make friction asymmetric in different ways. So there's the crab and a descendant of the crab. Here are some other robots that again all seem to do more or less the same thing. This was back in 2000, so physics engines weren't very sophisticated at this time. You can see there's a lot of interpenetration between the objects here. A pretty poor simulation. Okay, but again, evolution manages to evolve robots that work. So now let's get to the full reason why this was done. The researchers took some of these better evolved creatures, manufactured them using a 3D printer, and then measured how well they did in reality. We're going to look at 3 evolved individuals, and I've reported on the right here how far they traveled in simulation and how far they traveled in reality. If you look for a moment at the images of the physical robots, you'll notice all the white. That's white thermoplastic. So at this time in 2000, the 3D printer would print out hollow cylinders here out of this thermoplastic. We'll talk about the 3D printing in a moment. And then you can see the researchers snapped in the motors in these places. Let's have a look at these 3 different individuals. So let's start with the virtual arrow. And this one I'm going to have to play here. That's not what I want. Okay, here's the virtual arrow, which again is minimizing and making asymmetric friction to move in a particular manner. Here it is in reality. Looks pretty good. You get the same basic gait if you want. But you'll notice that it didn't do very well in reality, right? It traveled less than half as far as was predicted in simulation. Let's have a look at the pusher now. If I can find it. Apologize, I can't find the video for this one, but that's all right. I want to focus on the tetrahedron for a moment, which, as you can see from the numbers, actually did cross the reality gap quite well. Let's put this one over here. Oops. So there's the tetrahedron, and I want you to mentally compare this against the arrow. And here's the tetrahedron in reality. Okay. So the arrow failed more or less to cross the reality gap, but the tetrahedron did a fantastic job and was actually within 0.1 centimeters of, was within 1 millimeter of what was predicted in simulation. Exactly same evolutionary simulation, the whole process produced two different robots, one that crossed the reality gap and one that didn't. Now the million-dollar question, why? What is it about the tetrahedron that makes it a little more robust than the arrow? Number of motors, perhaps, right? So there's two motors, at least two motors in the arrow and just one in the tetrahedron. So the tetrahedron's simpler, which is definitely probably a big part of the answer. What else is different between the arrow and tetrahedron that may impact its ability to cross the reality gap?
So the arrow has a lot more points where actual friction would apply. The tetrahedron has less. So there's no way that you're going to have the same coefficient of friction between the simulation and any surface on the line.
Exactly. So one of the things that's particularly tricky to simulate is accurate friction or physical response to friction, right? A lot more points of contact. If you were to look at the distribution of weight and the direction in which friction is being applied in the arrow, it's a lot less and probably simpler than it is in the tetrahedron. If you look carefully, the tetrahedron also pushes against the ground more vertically than the arrow does. So it's sort of lifting up the tetrahedron and moving it. So it's almost to the point where it's lifting the whole thing up. That also probably makes things a little bit simpler in terms of simulating the friction. Again, it's hard to say. We just know that there are some robots that transfer better and some that don't. We're going to come back to this issue 2 lectures from now when we talk about the transferability approach to crossing the reality gap. We do know that a whole bunch of robots transfer well and some that transfer not so well. Can we actually learn features of robots that predict before we transfer them whether they're likely to transfer well or not? Okay. At this point, the GOLEM project was an attempt to try and cross the reality gap by just simplifying the crossing of the gap. So we're not trying to minimize the gap. The idea here is, well, let's just print out as many robots as possible by automating the manufacture of these machines, right? We're using, in evolutionary robotics, we're using evolutionary algorithms to automate the design of robots. And if we marry evolutionary algorithms to 3D printers, we can also automate, to some degree, the manufacture of those machines. Okay. So let's have a look at how this works. Again, this is This was the first introduction, more or less the first introduction of 3D printers into academia. Now they're almost becoming commonplace. What exactly was being printed? Well, remember the genotype was evolving the position of these vertices in bars. The 3D printer at that time was laying down layers of thermoplastic. So this is plastic that is heated up and has a low melting point. So it's actually a liquid and is deposited onto a plate. And as it's deposited onto the plate, it cools and solidifies. And then the next layer is deposited. And if you do this over and over again, this is a vastly sped up video. You can see, in this case, the 3D printer printing just one cylinder, which is all well and good. But what happens when you want a complex construction of all of these cylinders? One thing that you can do is print layer by layer the structure that you want. If there's some support material that's needed, you print very thin struts underneath. You then wash this in a solution bath overnight, and it will wash away this very thin thermoplastic, and you're just left with your robot. 3D printers have come a long way in 16 years. This is still a technique that's used, but there's lots of different ways you can 3D print items these days. Okay. The 3D printer here obviously is only printing the plastic skeleton of the robot. All the other material is embedded in there. These robots have ball joints, so not unlike your shoulder, your shoulder and hip joints. You'll notice that if you think carefully and creatively about the geometry of what you're printing, you can create a passive ball joint. And depending on the geometry of this aperture here, it can act more like a hinge joint or more like a ball and socket joint. So in Bullet, in our physics engine, usually these joints are discrete things. It's either a ball and socket joint or it's a rotational joint. But again, if you think carefully about how to manufacture this, we can make something that's somewhere in between a hinge joint and a ball joint. Okay. Then we snap in the motors and electronics, and away we go. Once you've done that, you can then, once you're finished with your robot, you can put it in. You can put it in a heater and reduce, reuse, and recycle. Again, a vastly sped up video here. Melt down the thermoplastic, collect it, and print another robot. And if all of the members of the media were not scared enough, they made this video, which is reduce, recycle, and reuse. Okay, just for fun. Okay, so we got a few minutes left. I'm going to show a short video with the actual investigators, the researchers of this project, telling you a little bit about a follow-on project, which is Fab at Home. So this was the beginning of open source 3D printing. So actually printing parts of your own 3D printer. I apologize for the audio here. Hopefully you can all hear this, all right?
There are a lot of ideas out there that people have and never get realized. And one of the things we wanted to do in this project is to provide a means for realizing physical objects.
This is the Fab at Home desktop 3D printer.
We really don't like to think of this as a product because we're not selling this. We just posted the blueprints for this online.
The way the Fab at Home works is just like an inkjet printer.
You design your concept, your idea, in some software package with multiple materials, liquid materials, materials that conduct electricity. You hit the print button and you go get a cup of coffee.
And the syringe is loaded with silicone rubber, motor that drives the piston of the syringe to squeeze material out.
Most people on the street wouldn't know what a rapid prototyping machine is. If you look at computers, we have music, MP3s, photography, but making physical things, that's way behind. And so we hope that by making a kit like this to transition from an idea that's modeled in some software, and there are plenty of these, into a physical object with minimum effort, people will be able to work with this, build it at home, modify it, play around with it. It's an open source, hackable system. You know, you void your warranty if you put chocolate in your commercial rapid prototyping machine. But here, if you want to print chocolate, you can put some chocolate in it.
You see new, great creative ideas come out of something as simple as this.
The vision of using automatic factories to aid space exploration, so that on distant planets, machines could be churning out exploration robots, and they would do their bit and learn about the environment, and then a newer, improved version could be made right there on the spot. We've shown that you can make more than just a cell phone case. You can print out transistors, you can print out batteries, so you could print the whole cell phone in the near future. This is a way for people to become inventors of technology rather than consumers of technology.
I truly believe that in 20 years or so, many families will have a fabricator in their kitchen that will allow them to download blueprints.
Okay, so this was the Fab at Home project that followed on shortly after the GOLEM project, which was, again, an attempt to try and allow people to make their own 3D printers, which now exist as kits. This was a project at Cornell. At the same time, across the pond in England, the RepRap project was going on. We only have a few minutes left, so I won't play this video. You can go and watch this on YouTube. The RepRap project was an attempt to make a 3D printer, and that 3D printer should be able to print out all of the parts from which it's made. And then it's still, at that point, relied on a human to put all the parts together, and you have another version of the 3D printer. We got 2 minutes left, so I want you to turn to your neighbor and think about this question. So imagine you have a RepRap that can print out all of the pieces to make another RepRap. Let's imagine we wanted to evolve 3D printers to make this self-replicating process easier, faster. We could evolve the 3D printers in different directions. If you could apply an evolutionary algorithm to a 3D printer that prints a copy of itself, what would the fitness function be? Okay, spend a couple minutes thinking about that. We'll see what you came up with, and that'll be it for today.
Yeah.
Right. Something that could maintain the same string of its it's better than trying to think of a way to use materials for something that have like some kind of structure.
Okay, so we have a 3D printer that prints out its parts and relies on a human to put all those parts together, and then the new machine prints a copy of itself, and so on and so forth. How would you apply an evolutionary algorithm here? What sorts of properties of this replication process would you want to optimize?
So we'd want to optimize, first and foremost, fitness would be whether it can make another copy of itself.
Sure.
Like, does it work, basically?
Right, we could start with a 3D printer that doesn't print out all the parts, right? We could maximize the fraction of parts that it manages to manufacture.
And then also the amount of materials that it itself takes.
Right. So we talked about the support material that has to be washed away, right? So it's still a relatively inefficient process. Can it print and waste as little material as possible?
The less parts, the better.
The less parts, the better, right?
You also want durability.
Durability, right? So make a machine that's print a copy that's as durable or maybe even more durable than the machine that printed it.
How fast it can print.
How fast it can print it. What else?
The cost of the materials.
The cost of the materials. How green are the materials that it uses? How much energy does it use to do so? We could actually imagine, again, not using today's technology, but maybe in the not too distant future, machines that print better versions of themselves by placing the replication process itself under evolutionary control. There are obvious ethical issues around whether we would actually, as a society, want to create self-replicating machines. This is an idea that's been always very popular in science fiction, but now we're coming to the point where we have to think about whether we actually want to go about instantiating this kind of technology. I'll leave that as something for you to think about. Okay, you got a quiz due tonight. Please read through the final project document, and your first report will be due Monday night. See you Tuesday.